Today I want to teach you something about flow losses in pipe systems. Here you see a really simple pipe system. It is a shower water system, and it is a pipe system for the cold water that comes here from inside the house and to the valve of the shower, and you will inject the hot and cold water and you will mix it here in the armature. But what happens if someone flushes the toilet? The water will be hotter. And why is it like this? It is because when you open the valve to the toilet tank and you fill up the tank with cold water, then you get a pressure drop into the inside the pipe system, and the amount of water that will flow to the shower will be less, and so you have too much hot water and the mixing temperature will be hotter. So we come to the very famous law of Daniel Bernoulli. He lived from 700 to 782, and he was a famous scientist who discovered a lot of laws in fluid flow and in physics, and he described a lot of these laws with mathematical formulations. And here you see the most famous Bernoulli's law. We have the pressure on one side, we have the density divided by square of the velocities, and we have the pressure of the height. It's rho times g, gravity constant, times the height, and so you can calculate, and this should be always constant. It's an energy equation, and this amount of energy should be the same if you enter a pipe and up to the exit of the pipe. But that is not always really true. Sometimes you have always also losses in the pipe system. You lose energy, and you can lose it by velocity losses, or by pressure drops, or by any narrow angle where the fluid has to go around the edge or into the armature. That's something we want to have a look now. Here's a picture I show often. It's a really famous museum in Istanbul. I lived a long time in the city of Istanbul, and you see here we have a pressure. We have also our dynamic. We call it the dynamic pressure, the half of rho velocity squared, and we have the term for the height, rho times gravity constant times height, and on both sides it should be the same. We have here the index 1, and on the other side the index 2. And why has the artist placed this big formula on the wall of a museum near the Bosporus? Because the water enters the Bosporus and it exits the Bosporus, and you will have an energy balance between the entry of the Bosporus and the exit of the Bosporus, and more or less it should be the same energy if you enter. But of course it will not be totally the same, because you will have losses from the walls of this big stream, from the stones. And I can tell you, I had a friend in Turkey, and he was also a professor and scientist, and he examined the turbulence on the ground of the Bosporus. He made measurements for the turbulence there. And here I want to show you someone. I want to mention him. It's Gottfried Wilhelm Leibnitz. And I want to mention this scientist. He lived from 1646 to 1716, And I want to mention this person because he discovered the same law. So he also discovered Bernoulli's law, but Bernoulli's law